Okay, in this podcast, we're going to learn how to calculate average atomic mass on page 6 of our packet. And we are going to fill out all of it. Actually, I'm going to ask you to do one of those questions yourself, but all the way from the top to bottom should be filled out in order to get your stamp. And actually, before we start on the packet itself, I wanted to show you something. This is just a little kind of simulation, but it has a really good visual depiction of how different elements have different isotopes, just naturally in nature. Magnesium, which is this example I pulled up to start with, has 3 different natural isotopes. And when you have a chunk of magnesium, you're going to naturally have a mixture of all 3 isotopes in there. And so if you just react a chunk of magnesium in the lab, it's not going to be pure one isotope or the other. It's going to be a mix. And if we needed to use the mass of that magnesium to do some calculations, we'd have to use the average mass of all of the atoms that might possibly be in my chunk of magnesium. So you'll see down here on my slide, the average atomic mass is written here, 24.305. That's what you'd see on the periodic table. And that's because we've got a mixture of magnesium 24, magnesium 25, and magnesium 26. And if you look at the abundance in this little pie chart up here, most of our magnesium is magnesium 24. So it makes sense that this average is closest to 24, because that's what makes up most of our mixture. So that's the number we're going to be calculating. And if I clicked around, I could show you a couple other atoms. Hydrogen has 2 isotopes. Lithium is 2 isotopes, although one is major majority. Beryllium only has 1 isotope. So clicking around, seeing some of these. Aluminum just has 1. Some of these only have 1 majorly stable isotope and just a very small amount of some of those others. But just kind of some cool information. Okay, now let's get started with this calculation stuff. Back to these slides. So, at the top of your page, it asks us, there we go. It starts by telling us a little bit about the average atomic mass and how we're going to be measuring it in AMUs. That's our atomic mass unit. It's just standardized as 1 proton or neutron should weigh 1. Makes it easier than writing out the actual mass of a proton, which is technically, say that 1 AMU, 1 proton or neutron is 1.673 times 10 to the negative 24th grams. And if we had to do calculations with scientific notation and averaging those out, it'd be a headache. So it's a lot easier just to use AMUs. You'll also see those as just U here. That's what these units for mass are. So that's all that the top really says. We're going to jump straight into actually doing this calculation and finding this average. And this average isn't going to be like most of the averages that you take. There's 3 specific steps we take, and it's not add them up and divide. So get that out of your head. Calculating the average mass is going to be different because we can't actually physically count up and add up the mass of every single atom. Even a tiny chunk of material is going to have millions and billions of atoms. So we're going to have to use the percent composition information, like what we saw in that simulation earlier, and the actual mass of a given isotope. And what we're going to do with those 2 pieces of information, first, we're going to turn the percent into a decimal by moving the decimal left 2 times. So we're just dividing by 100 here, getting it out of percent form into its decimal form. Then we're going to take that new percent with its decimal in its new place and multiply by its mass. You're regularly going to see these depicted like you see here in kind of rows and columns. And so in general, that means you're going to be multiplying your rows together and then add up the products of each row, and that'll give you your answer. So if we go through that process with this first one, my first step is to move my decimal. So I'm going to put that here, move twice on each of my percents. And then I'm going to multiply this first percent by the mass that it goes with, and that equals 43.5353144. Keep as many numbers as you can for right now. We will round it at the end. You got a lot of sig figs here to start with that. And technically these percents are exact numbers, so you shouldn't round to 4 sig figs there. I'll talk about rounding when we get to the end. But this second row, when I multiply that new percent by its mass, we get 20.01723858. I moved my decimal, multiplied my rows. Now I just need to add up these two products to get my answer, which is 63.552555298. So now, like I said, rounding with these are going to be a little bit weird, and sig figs and stuff it depends on how carefully you measure these masses. So really, in general, once you do your math and you come up with your answer, we're just going to tell you to leave about 2 decimal places. Never round these to a whole number, but also probably don't need to write out all of these numbers. So you could probably have kind of stopped writing any of these numbers and left off these last kind of 4 digits if you wanted to, because I'm just going to expect you to have at least 2 digits. So I do want you to make sure that that's rounded appropriately and short, just a reasonable number of sig figs and decimal places. So my correct final answer would be 63.55 AMU. And if I'm trying to make sure that I have that right, if I go back and I look at my original numbers, this element, the isotope with the highest percent, should be what my answer is closest to. Is my answer closest to 63? Sure is. So I'm pretty sure this is correct. So let's do that same thing again. So our first step is to move the decimal left 2 times. And in this first one, that's easy. I need, there we go. Back to it. Moving the decimal here. But on the second one, don't be tricked. You have to move it 2 times, which means I'm going to have to add a 0 here. Same in that next number. I have to add a 0 to make sure that that decimal has actually moved 2 times. Just going to clean this up a little bit. Okay, so I've moved my decimal. Now I'm going to multiply my rows together and get those products out for each row. And I want you to try multiplying this, making sure you're getting the same answers that I am. So all that multiplication gave me a whole lot of numbers here. And now my last step is add them up. And after I've done that, then that is going to be my final answer. And that should be 20.18 once we've added that all up and rounded it out. Technically, that came out to 20.179444631. But if I just wanted to keep those first 2 decimal places, then the 9 would round that 7 up. Remember, we're not just going to cut anything off. We are always rounding things off when we kind of shorten them down. And so even though we only want to keep 4 sig figs or 2 decimal places here, then we're going to keep rounding that off. And of course, that would have the units of U or AMU, whichever one you want to use there. Checking my answer, my highest percent abundance was pretty much 20, and my answer is pretty much 20. So, looks good. I feel confident in my answer. I am going to ask you to do this next calculation. Same process we've gone through before, slightly different numbers. Just move your decimals, multiply, and add, and get that final answer. Check your answer. Not telling you what it should be, but it should be closest to 24 compared to all of these other numbers. So do that to get your stamp. But together, let's go ahead and answer this last question at the bottom. This says the element boron has an average atomic mass of 10.81. However, no single atom of boron has a mass of exactly 10.81. Explain why. Well, I think I just mistakenly added in a key word there. A lot of times we'll talk about the atomic mass just like that, instead of using the word average atomic mass. It just saves time and space. But because of that, people think that an atom has a mass of that number, but it's not. That atomic mass on the periodic table is an average of all boron atoms, not just the measured mass of a single atom. So that's like me saying, oh, the average weight or mass of a student in my class is 132 pounds. Does that mean any single student in my class weighs 132 pounds? No, that's just the average. It's the kind of compromise number of all of the numbers in the class. So get that down, make sure you did that previous calculation, and we're done. Get ready to do some calculations in class, but they're pretty straightforward, pretty simple compared to the last set of calculations we did, right? Have a good rest of your weekend.